Alright, so picking up with section 6.2 in the practice test, it says state if the given functions are inverses. And how do we do this? Well, here's the condition for something to be an inverse. We need to be able to say this. We need to say if we plug in h of x to f, we should just get x. And the same thing, if we plug in f of x to h, we should get x. In other words, everything should cancel each other out except for the x's. It's like you plug something in, you do something to it, and then you reverse the whole process. So let's test this out. Let's find, first of all, f of h of x. So that means wherever I see an x up here, I should now plug in this entire function. So let's try that. The cube root of negative, and then I'm not going to plug in x now, I'm going to plug in an entire function h of x, negative 2 minus 2x cubed. And let's simplify that. So we get the cube root of, this thing is still over 2, and then if we distribute that negative right here, we would get this. Okay, we would get positive 2 plus 2x cubed minus 2. 2 minus 2, well, those cancel, so we're left with the cube root of 2x cubed over 2. Those cancel, so we're left with the cube root of x cubed. And cubing something and cube rooting cancel each other out, so that just leaves us with x. So at least it passes the first condition. We know that f of h of x equals x. We have to do the opposite though, because this has to work both ways. It passes this condition. The question is, does it pass that condition? So let's test that out now. So we'll just move this down. So we have, now we need to test h of f of x. And h of x is this function. It's negative 2 minus 2x cubed. But instead of x, now wherever I see an x, I'm going to plug in this f of x function right here. So that's going to go up in that parentheses. So I have the cube root of negative x minus 2 over 2. So this is going to equal negative 2 minus 2, and then cubing and cube rooting cancel each other out. So that just leaves us with what's inside the cube root. Then we have the 2 times 2, that will cancel. So we're left with negative 2 minus negative x minus 2. Let's distribute the negative right here. Negative 2 plus x, and then plus 2, and sure enough those cancel, and we're just left with x. So since both compositions, both f of h of x and h of f of x, that's called composing a function, since both of those canceled everything out except for the x, the answer is yes, they are inverses. If that hadn't worked, they would not be inverses. Okay, next question, how do you find the inverse? Well, the easiest way to find the inverse, this right here is really interchangeable with y. An inverse means opposite. So if you want to find the opposite, you would switch things around. You would flip the x and the y. So this y is going to be swapped with x, and this x is going to be swapped with y. And now all we need to do is solve for y. So we'll solve for y by adding 3 over 2 to both sides. So we get x plus 3 over 2 is equal to 3 over 10y. See what's being done to y and do the opposite. Y is being multiplied by 3 over 10, so we want to divide by 3 over 10. But dividing by 3 over 10 is the same as multiplying by the reciprocal, which is 10 over 3. So those will cancel, just leaving us with y. And then let's multiply this by 10 over 3. If we distribute right here, we get 10 over 3x. Just box that off, that's a separate problem right there. 10 over 3x plus, and then the 3's will cancel here. The 2 becomes a 1, and 2 goes into that 10 5 times. So that's the same thing as 10 over 3x plus 5 equals y. And then generally speaking, we don't say y when we're talking about inverses. We say f inverse, which is f with that little negative 1 here. So that should be the inverse function. Let's check to see that we got it. We did. The only difference is they put the 5 in front and the 10/3 x second. We just had it swapped, but it doesn't matter. Alright, how do you find the inverse and then graph it right here? So this would be easier, and this is a calculator problem. This would be easier to graph this on a calculator. But in general, inverses, when things are inverses, you can kind of see all these graphs, maybe with a couple exceptions. There's going to be kind of a nice symmetry to it, and we'll see that in just a sec. So first let's find the inverse of g of x. Remember that g of x or f of x kind of is interchangeable with y. So then to find the inverse, we'll just swap these. The y is going to be swapped in exchange for x. And then we have the fifth root, not of 16x now, but of 16y. And that's all over 2. So now we need to get at that y that's kind of buried inside the fifth root. So let's do this. Let's multiply everything by 2, so those will cancel, and that becomes 2x. And then we have this thing still left over. Then let's subtract 4 from both sides. We get 2x minus 4 equals negative fifth root of 16y. We just want a positive fifth root, so let's divide by negative 1. That will cancel. We divide this by negative 1 also. 2x divided by negative 1 is negative 2x, and negative 4 divided by negative 1 is positive 4. So we have this right here. Okay, now to cancel out the fifth root, we need to do the opposite of fifth rooting something, which is raising it to the fifth power. Okay, and just to make this a little bit easier, before we raise this to the fifth power, let's pull out a negative 2. So if we factor out a negative 2, that leaves us with x, and then 4 divided by negative 2 is minus 2. So again, why are we doing that? Just to make it easier to handle. And also, if you look at the options here, when we end up seeing the options, if we didn't do that step, it would be harder to pick out which is the right option. So from those multiple choice. Okay, so now we're taking, we said that we raised the other side of the fifth power. Now we have to raise this side and use a different color so it's easier to see. We have to raise this side of the fifth power also. Negative 2 to the fifth power is negative 32. And x minus 2 to the fifth power, we'll just keep that as is. Fifth rooting and raising something to the fifth power cancel each other out. So now let's solve for y by dividing by 16. On this side, negative 32 divided by 16 is going to be this. Let's just put it over here. It's going to be negative 2 times x minus 2 to the fifth. And that's going to equal y, but we want to replace y with f inverse to signify that's the inverse. So that's what it looks like. If we look at the multiple choice options, the only one that's even recognizably like that is B. And these you can just plug into a calculator to graph it. You can see this is kind of the symmetry I was talking about. This inverses are reflected over that line, which is the line y equals x. And here's kind of an intuitive reason why. Inverses are when you swap the x and y. So if you reflect it over the line y equals x, if you swap x and y, you get that, which is really kind of the same as that. So that's kind of an intuitive idea of why inverse graphs are symmetrical like that. Alright, find the inverse of the function. We said inverse means opposite. So the easy way to do this, these are xy, those are xy pairs. How do we find the inverse? We just switch the xy pairs. So the first one, if we switch 1, negative 7, we would get negative 7, 1. We switch negative 2, 4, we get 4, negative 2. And the last one, you can see right there, 5, negative 8 would be the switch. Okay, let's graph these right here. So let's just pull up a graph real quick. Use this one, use the second one here. So we want to graph each of these, and the easiest way to do this is to know what the graph of square root of x looks like. This is called a parent function. So y equals the square root of x, the graph looks like this. The square root of 0 is 0, so that's going to be a point on the graph. The square root of 1 is 1, so that's a point on the graph. The square root of 4, so there's x equals 4 right there. The square root of 4 is 2, so that point is on the graph. And then you just kind of connect the dots like that. That's what the parent function looks like. We can't take the square root of negative, so that's why this entire region of the graph is empty right there. And that's going to help us answer these questions about domain and range also. So what I'm going to do is I'm going to draw the parent function, which we just drew. Okay, this graph right here, that's y equals square root of x. That will help us draw this graph. So this graph right here, it's going to be, you may remember this from prior sections, add to x, go left, and add to y, go high. That tells us how graphs are transformed. So this right here, we're not adding to x, we're subtracting, so that means go right 1. So I'm going to take this point, I'm just going to shift it to the right 1. Okay, and then the other thing is this right here, add to y, go high, that means we're subtracting from y, so we're going down 3. So we went right 1, down 3, and that blue dot that you see right there, let me erase this, and actually I should make the other one red so it doesn't confuse you. Okay, that point right there is the new vertex. Okay, this basically what this means is if you want to find the vertex, you see what value makes that 0, and the answer is 1. And then if this whole thing is 0, 0 minus 3 would be negative 3. So this new vertex right here is at 1, negative 3. And that means all these other points did the same thing. Right 1 down 3 for this one puts us here. Right 1 down 3 right here puts us there. And that's what the graph is going to look like. It's been shifted to the right 1 and down 3. What's the domain and the range? Okay, well, the domain is going to be anything basically where x is greater than 1. Domain is x greater than 1. Why does it have, or I should say greater than equal to. Why does it have to be greater than or equal to? Because if you look at this right here, x minus 1, what would make that a problem? If that thing were less than 0, you'd be taking square roots of negative. So we just need to set this equal to 0, and then we see that x would be 1, basically. When x equals 1, you'd be taking the square root of 0, so x has to be greater than that. Okay, what's the range? The range, which R stands for range. Range is basically anything above this vertex point. Okay, so really all we need to find the domain, the range, is we need this vertex. X is going to be greater than the x coordinate, that's the domain, and the range will be y is greater than or equal to negative 3. Because you can see from this graph it never goes down here, it never goes below negative 3. Alright, let's do the same thing right here. So first thing we'll do is find the vertex. The vertex, what x value would make that square root 0? Negative 4. What happens to the y if this is negative 4? Well, you'd have square root negative 4 plus 4, that's square root 0. Minus 3 would be negative 3. So there's the vertex at negative 4, negative 3. And we know the square root graph goes roughly like this. As long as we're fairly close, that's good. The domain is going to be x is anything that is going this way. X is anything greater than negative 4 or equal to negative 4. Why does it have to be greater than or equal to negative 4? Because if you put something in here that was less than negative 4, you'd be taking the square root of a negative. And the range is anything that is above that y value. That y value right there is negative 3, so y could be greater than or equal to negative 3. So that is section 6.2 and 6.3, and the next section we'll start talking about 6.4 and following, which is where we simplify square roots. So we'll see you in that video.